So hello everyone, this is lecture 2 for the nuclear physics. In the first lecture, we have seen the complete syllabus which we are going to cover in this series. So today we are starting actually the basic properties of the nucleus. So first let's understand what is atom and what it is made up of. So atom is neutral, you already know, and what is inside the atom is nuclei and the electrons. And if we talk about electrons, you already know that is have the negative charge. Mass of electron is nothing but 9.1 into 10 to the minus 31 kilogram. So you must know all these numbers which I am mentioning here. And charge is minus E, and 1 E is nothing but 1.6 into 10 to the power minus 19 coulomb. And if we talk about nucleus, then it contains protons and the neutrons. And proton, we talk about, then charge is positive E equal to the electron, and that is in the positive. If we talk about the mass of proton, that is 1.006 AMU, that is atomic mass unit. We will understand more about it later. And if we talk about the neutrons, the neutrons are neutral, and that doesn't mean that they haven't any charge. It means that there is equal amount of positive and negative charge inside the neutron that make it neutral. And mass of neutron is nothing but 1.007 AMU, a little bit larger than proton. And both mass of proton and neutron is very much larger than mass of electron. And that's why we will say that most of the mass of the atom is concentrated in the nuclei. And both combined, the proton neutrons inside the nucleus is called the nucleon. And how we denote a nucleus, that is by this X. Z denotes the protons, means the atomic number, we also say that. And this is number of neutrons, and this combined will give you the atomic number or the mass number that we denote by A. And this nucleus is very highly dense. The densities came out to be approximately 10 to the 17 kilogram per meter cube. This is means the star have the same density around this. So there is nothing on this earth which has density around this. So this is comparable to stars. And this is your A, that is mass number, is nothing but Np plus Nn. This is number of neutrons and number of protons. And if we say that what is the number of neutrons, that is A minus Np. And if you subtract minus Np both sides, it will give you Nn minus Np. And Np is nothing but Z, that is atomic number. So A minus 2Z. So this is the difference between the neutrons and the protons inside the nucleus. And you will see this term many times inside this nuclear physics. So you must remember this thing. The difference is denoted by A minus 2Z. Now see, as atom is neutral, so Q positive must be equal to Q negative, means number of protons multiply E plus number of electrons minus E must be equal to 0. That gives us the number of protons must be equal to number of electrons. You already know that. Now you must remember these two numbers also. The radius of nuclei is approximately 10 to the minus 15 meter, that is Fermi, around the Fermi meter. And A naught, that is the radius of atom, that is 10 to the minus 10 meter. Now let's discuss some different properties. First we will study about the nuclear mass. So what is nuclear mass? Nuclear mass, or the masses of different particles like proton, neutron, etc. We represent it by the AMU, that is atomic mass unit. So this is nothing but a unit of mass. And 1 AMU is equal to 1.66 multiplied 10 to the minus 27 kilogram. So you must remember, wherever we are using AMU, you can just multiply with this number and you will get the mass in the kilogram. And if you see inside the nucleus, the mass and the energy are equivalent, means you can convert mass to energy, energy to mass. So only in the nucleus. And the equivalent energy of this 1 AMU is nothing but m naught c square. So this is the rest mass energy. So you will just substitute this mass and c square and divide by the 1.6 10 to the minus 19 to convert into the electron volt, and divide also by 10 to the 6 to make it a mega. So it will be 931.5 mega electron volt. So this is 1 AMU correspond to this, means this is not equal to this. This mass is equivalent to this energy. So you must remember this difference also. Now see, normally what we do that mass of nuclei equal to mass of proton plus mass of neutron, that will give you the total mass of nuclei. But this is not the case inside the nucleus, means mass of nucleus will always be less than the total mass of proton and neutron combined. See why it is so. As you already know that anything inside the bound motion, which is means sometime it will be at the free movement. Now when it comes to the bound motion, it will lose some energy, and that's why it gain the negative energy. As we already know, in the hydrogen atom, the minimum ground state energy is minus 13.6, and all the bound state systems have the negative energies. So that is nothing but means they are devoid of some energy, means if you give this amount of energy, it will become free. So where this energy coming from? Inside the nucleus. So this is coming with the expense of mass, means when these are come to the together, means all the particles come together, then they are bound only because of the some energy is released. and that energy is released because of the mass of the proton or neutron. That's why this combined mass will be less than the total mass of nucleus, and that energy or that mass will convert into the energy, and we also call that as defective mass defect, and the energy which is expand is called the binding energy. So mass of nucleus is nothing but equal to ZMP, that is Z is nothing but total number of protons, mass of proton, plus A minus Z will give you number of neutrons, mass of neutron. This is the total mass minus some mass defect, that will give you the total mass of nuclei, and this mass defect will convert into the energy, and corresponding energy is called the binding energy. So I hope you already know these things, but I just cleared it. Now next is we will discuss about the nuclear radius. So see, there is no derivation or something like to find the radius of the nucleus, but we did the experimental things, and according to the experiments we have find, and we fitted all the data into a formula, and we find that radius is proportional to the a to the power 1 upon 3, and a is nothing but mass number, that is number of nucleons. Experimentally, it was find out radius of the nucleus is proportional to a to the 1 upon 3, where a is mass number and radius is proportional to a to the 1 upon 3. Now remove this proportionality constant, means proportionality sign, and you will get this proportionality constant, that is r naught. R equal to r naught a to the 1 upon 3. Now what is the value of r naught? That is corresponding to 1.5 to 1.5 Fermi meter. And see, if in the question the r naught value is not given, then you will use the 1.2 Fermi. So if r naught is not given, then we will use 1.2 Fermi. You must remember this number. Next is nuclear mass density. So what is nuclear mass density? That is mass per unit volume inside the nucleus. So for that we need to consider all the mass and all the volume. So let us consider a spherical nuclei. So we are considering a spherical nuclei. It is not the case that always it must be spherical. It can be oblate also. But now we are here we are considering the spherical case. So this is your nuclei AXZ. So nuclear density is mass per unit volume. So mass is nothing but this is your total number of nucleons inside the nucleus multiply, we are thinking that mass of proton is approximately equal to mass of neutron. So that is total mass number multiply the mass of one proton 1.67 10 to the minus 27. Total mass of the nucleus divided by total volume of nucleus is nothing but 4 upon 3 pi r cube. Now substitute the value of r from here, and you will get a to the 1 upon 3 here, and that will cancel out, and a and a will cancel out. So you will get these terms remaining. Means r naught is nothing but 10 to the minus 15 we are considering, that is in the Fermi. So we will just substitute the value of r naught here, and you will get density as 10 to the 17 kilogram per meter cube. So we already discussed this number, and we now seen that how we find this. Next is nuclear number density. That is nothing but number of nucleons inside the means in 1 meter cube how many nucleons can contain is called the nuclear number density. So you know there is 10 to the 17 kilogram in 1 meter cube. So if you divide it by the mass of one nucleon, you will get the number of nucleon per meter cube. So the mass of one nucleon is 1.67 10 to the minus 27 density divided by this will give you 10 to the 44 nucleons per meter cube. So this is nothing but nuclear number density. Next is distance of closest approach. So this is the distance, means this is the distance measured by the Rutherford. He did the alpha particle scattering experiment, and he did this experiment, and in result he have just to find the result that what can be the radius of the nuclei and approximated that idea. So this result or this experiment was very helpful. So let's understand about this. So there is this alpha particle, there is this nucleus, and what is this alpha particle is? Alpha particle is nothing but the nucleus of helium, and nucleus of helium contains a +2 charge, and the mass of alpha particle is 4 multiply mass of one nucleon, because there are 4 nucleons inside the helium atom. So this is nothing but helium nuclei. So it will have the +2e charge, and it is now in the free condition somewhere, and that's why its potential energy is 0. And now what we did some give it the kinetic energy and throw it towards the nuclei. So it is going this way, and see there are containing the charges. So force between them will be electrostatic force, and electrostatic force is nothing but conservative force, and conservative force means kinetic plus the potential energy will always remain constant. So if this particle is thrown this way, then its kinetic energy will start to decrease and potential energy will start to increase, and at some point this kinetic energy will become 0, and the potential energy will become equal to kinetic energy. So at that point when kinetic energy becomes 0, then at that point it will turn around and it will go back, and this distance is called the closest distance of closest approach. So using this distance we can find the radius of the nuclei. Let's see how. At the turning point we will see that K means kinetic energy must be equal to the potential energy, that is R equal to x naught. And now you know potential energy is simply means charge divided by 4 pi epsilon naught and the distance between them x naught, and this is your kinetic energy. So we can find the value of x naught from here, and you will see that x naught is inversely proportional to m naught, m alpha and the v alpha. Means larger the mass, larger the velocity, the closest will be the distance. So we can just decrease the distance. Means for the particular atom, this distance some it will be finite, and for different mass and the velocity, this distance will be different. So we need to find the minimum distance to find the radius. So because we know this radius will always will be less than this x naught, so we will find the minimum value of x naught, and we can approximate the radius also. That's what the Rutherford did. So we assume we did this experiment for the gold nuclei, and that is 79, and velocity is, that is the maximum velocity we can achieve at that time, 10 to the 7 meter per second, and we have find the value of x naught from here, that is 5.9 multiplied 10 to the minus 14 meter. So see, this is a very small distance, and now we are sure that radius is must be less than this closest approach distance, so radius must be less than this. So it was a very useful result, which had the help of this we have find it, or the approximated the radius of the nuclei, that it must be less than this. So this was clear that radius of the nucleus must be less than this value. And after that there was some more atoms and the velocities we used and experiments we did with more further readings. We have find it that radius must be approximately equal to 10 to the minus 15 meter. So that's why this experiment was very helpful. So you must remember all these things, they can be asked in the interview. So that's all for today. Thank you everyone.